and he works on privacy also from a legal perspective often. And so it should be interesting to see the follow-up to what Moon just set up for us. Let's welcome Aloni.
Thank you. So yeah, I couldn't have asked for a better setup because I didn't have to do all the hard work of explaining everything about redistricting. Yeah, and I guess just as a very brief intro, my background is cryptography and privacy. And I got exposed to this because Moon and I met at a workshop in Israel 3 or 4 years ago. And I knew things about differential privacy and she knew things about census, and we sat next to each other at dinner. And then we started talking. But yeah, so Moon mentioned that when differential privacy was getting adopted by the census, there was some worry from civil rights groups. There was a bit of a kerfuffle, not just from the civil rights groups. So I'm going to tell you a bit about that kerfuffle. A kerfuffle is also just one of my favorite words. So I'm going to just start with, it means, I don't know, I put a definition in my abstract, like a disagreement that stems from differing views, a brouhaha, a balagan, if you speak Hebrew. So anyway,
in your abstract, it says a kerfuffle is a commotion or fuss, especially one caused by conflicting views.
Right. And the example sentence was,
there was a kerfuffle over the use of differential privacy for the 2020 census.
There you go. Thanks. All right, so that's what a kerfuffle is. So let's start with confidentiality. So the Census Act from 1976 says that the Census Bureau may not disclose information reported by or on behalf of any particular respondent. This is the law that says that the data that the census collects has to be kept private. It wasn't always this way. I was very surprised to learn when I read more about this. 100 years ago, even less, this data was just not kept private. So anyway, this is what the law says. And there's basically one good Supreme Court case that interprets this law. And in this case, there was two cities that wanted, maybe a city and a county, they wanted access to the census's address file, like where are houses? That's what they wanted. And not counts, not population counts, not race and how many people live in those houses, just where are the houses? And the court said no. The court said even this, the census has to keep confidential, because that law that I just showed you doesn't just require the identity of the individuals to be confidential. It's any information disclosed by those individuals. So the master address file depends on information disclosed by individuals. So even that had to be held confidential. And it didn't matter what the cities wanted to do with this. It didn't matter that they only wanted to use it for statistical purposes and not to, find people breaking their leases. So that's what the census has to do vis-a-vis confidentiality. The census, as we'll get to, announced that they were going to use differential privacy as their main sort of conceptual framework for disclosure avoidance in 2020. And the main character maybe in the kerfuffle, one of the main characters is this guy named Stephen Ruggles, and he said, well, this is silly. It's based on a misunderstanding of the law, of the confidentiality requirements. He says that to comply with the law, it's not necessary to mask the characteristics of individuals. Rather, it's necessary to mask the identity of individuals. And if you read sort of everything that Ruggles and others put out, it seems like they would support a view that says, let's make lots of the data just public. That would be in compliance with the confidentiality requirements. I think it's pretty clear that Baldridge v. Shapiro says, no, not even the master address file can be made public, let alone the characteristics of individuals without their identities. So this is the confidentiality sort of debate. What are the requirements, and did the old techniques satisfy them? So what were the old techniques? The census used to, for 30 years, use lots of techniques. One of them was swapping, where they would move houses between blocks based on some certain characteristics of those houses. So if you were like a racial or ethnic unique racial or ethnic house, you had a higher chance of getting swapped. And they swapped you with a house that shared some characteristics and then reported aggregates based on that swap data. So that was one of, but not the only thing that was involved in disclosure avoidance for 30 years. And that was all well and good until the census came out. And this is John Abowd. He's the chief scientist, was.
Once he was replaced by Sally Keller about 3 weeks ago, I think.
3 weeks ago. So John Abowd was the chief scientist and was really one of the big forces at the Bureau, as far as I could tell. So just to be clear, I've never been in the Bureau. I mean, physically I've been there, but I've never been part of the Bureau. So I don't know anything that is really internal. But he seemed to be one of the big forces here. And so he reports originally in a tweet that the Census Bureau ran a Reconstruction attack. So let's look at the published statistics, come up with some set of underlying microdata that could explain those statistics. That's Reconstruction, a consistent set of census responses. And so Census ran a Reconstruction attack. And they check the accuracy against the data that they have, and they found that 46% of the total population was exactly reconstructed, and that sounds really scary. And I do want to say that this Reconstruction attack, and when more information came out about it, the more information was sort of received without much skepticism by the academic differential privacy community. And I think that was maybe one of the missteps in this kerfuffle from the differential privacy side. And Ruggles made a good point, whether a conceptual point, conceptual critique. Whether quantitatively his critique holds water, that's a different question. But at least the conceptual critique is, how big is this number 46%? Are we comparing it to 0? Are we comparing it to 35%? Are we comparing it to 40%? What's the baseline here? And somehow the question that's being asked is, what might we be able to, what number can we achieve if the census didn't output data? And that was a very good conceptual critique. And he made it in a expert filing, in his expert sort of testimony. In this lawsuit, Alabama sued the Department of Commerce, which is the federal agency under which the Census Bureau is housed. And in that lawsuit, Steve Ruggles gave his expert report. And in that expert report, he makes this critique. So let's just sort of unpack it a little bit. Here's what the census did. They started with people. This is data collected from 2010. They aggregated and published some of those data. And then they reconstructed some consistent database, D prime, that's consistent with the published statistics. And they counted the number of matches. They got a number, 46%. So Ruggles said, and I'm taking this number from a later paper, Ruggles said, well, if I just sort of know what types of people exist in the world, then I can sample random people without looking at the published census tables, get some other database D prime. There's supposed to be an arrow here. Maybe it'll appear. No, there's supposed to be an arrow here. Count matches. And according to Ruggles, you get 41%. So we can't compare this 46 to 0. We should really be comparing it to 41. That's sort of the conceptual content of the critique.
Where does this original data come from
data?
to get the 41%? Like, what are they using?
This data here.
Oh, okay. That's what you, yeah.
Are you asking, or did I answer the question? Or are you asking where this comes from?
I'm asking like, and where does it come from in the world? Because I would think of like, where else?
Right. So it also comes from census publications.
Census.
Exactly. So there are many conceptual and quantitative problems with this critique,
okay.
But it's still sort of something that has to be wrestled with. I would say. I don't want to get into it. As you'll see in this talk, I'm going to touch on a lot of things and not get into any of them. But even if you don't really get into this, so the point Rachel is making is this data itself comes from census data. So if census publications have always been disclosive, and you're trying now to say that the census publications aren't disclosive, it's sort of unkosher to use a census publication and say that if I just have this data, then I can basically get the same accuracy as I can get from this data, and therefore this data is not disclosive, right? You're assuming that this data is not disclosive, but if census data had a disclosure problem, then census data may have had a disclosure problem here and here. There's a epistemic problem here. Okay, but anyway, I don't even want to get into that. So Ruggles expert filing came 3 days before the deadline for amicus briefs, and there were a bunch of DP people writing an amicus briefs in support of the census's use of differential privacy. And so we had a few days to scramble to figure out how to respond to Ruggles' critique. And so one thing we figured out is, so this comes from the census's Reconstruction experiment, where they break down the reconstruction rate, this 46%, by the number of people within a census block. So the rate of reconstruction, this 46% number for blocks with 0 to 9 people in them, was something like 23%. It's not clear. This is all the information we have, so you can eyeball it. And for blocks with very many people, it's 60-ish%. If you rerun what Ruggles did, and you break it down by block, then you get something that looks like this. That on big blocks, Ruggles' method works very, very well. But on very small blocks, Ruggles' method works very poorly. And if you want to understand why this is, let's say you're playing cards and your opponent has a 20-card hand. You can guess a lot of the cards in their hand just by chance. And if you're playing Hold'em and your opponent has 2 cards in their hands, it's very hard to guess something in their hands. And that's what's going on here. Yeah, Moon, go ahead.
This is literal census blocks, right?
These are literal census blocks.
But then there's also, okay, I'll just maybe ask you later, but the big ones are usually group quarters, are usually like prisons and dorms. And so those are also special.
Or like a high rise.
Yeah.
Yeah.
But so those are also special, right? Those aren't just big. They also are special in other ways.
I'm sure that's true. Yeah. Yeah, I'm doing something very coarse here. You're saying you could do better on such blocks because you know things about them. Yeah, the argument that was being levied here was a very simple argument, and therefore, one should contend with it. But I think the deeper point you're making is there's a lot more information that one could use both here and here, frankly, right? If you're trying to show that these publications were disclosive, you can make use of plenty of other information in this reconstruction step. The thing the census did was just completely oblivious. Find some microdata that was consistent with the underlying publications. In fact, there's a paper posted on arXiv, as I think yesterday, by, I don't know, Cynthia Dwork, Aaron Roth, Michael Kearns, and maybe 4 other people that basically say, hey, let's put a bunch of other information into this step and see how well we can do. I haven't read the paper, but I think they say that you can do very well, very much better than this sort of 46%. I'm not exactly sure what that paper says because it literally came out last night. Yeah.
So for the argument of
For the argument of
Ruggles, did he say assume this minimum block size?
No, Ruggles just reported this aggregate. In his expert testimony, not this number, but this comes from the later paper, which is, the weighted average weighted by a number of blocks with these populations of these red bars, right? But the point here is that the reconstruction works, pretty well for small blocks, where this sort of random oblivious thing doesn't work at all for small blocks. And Alabama was the state at issue in the lawsuit. I don't remember exactly, but I don't know, maybe it was 20% of blocks were 50 people or less, some large fraction of blocks in Alabama. So in any case, the census announced that they're going to use differential privacy. as their sort of conceptual framework for the 2020 census. If I say anything wrong, just jump in.
No, you're doing great.
All right. So what's differential privacy? It was defined yesterday. Basically, it's a definition that says an algorithm is differentially private if when you run this algorithm on a data set or a data set with one person's information removed or changed, the output is basically the same. I'm not going to get into details. They're not going to matter for this talk. So the census wants to use differential privacy. They have to build an algorithm. I'm sure Phil will tell you all about that and how what went into the making of that algorithm. I'm going to say very little, but how does this algorithm, the top-down algorithm, work? They take the data, the census enumerated data. They add some noise to that data, and then they post-process to make the resulting data sort of nice. So make the resulting counts non-negative, make them all consistent, make them integers, satisfy various invariants and constraints. And then you do this for the national level, and then you do it for the state level. You make sure that these counts are consistent with these counts. And you do this down the census hierarchy that Moon mentioned, and you get down to the block level. And then you, at the end of this top-down algorithm, is why it's called that, you have noisy microdata. You have sort of synthetic microdata that is consistent with sort of many of these noisy statistics, is close to these noisy statistics. So I just want to look at an example, and this is everything I'm going to say about top-down. So here's an example. This is the enumerated counts. This is the input to the top-down algorithm now sort of at the block level. We've imagined that we've done the nation, the state, the counties, the tracts, the block groups. So we're at the block level. And let's just look at, for example, the population under the age of 18. So in this block, block 1, there's 25 people. How much noise is added to these counts? You sample this from an appropriate probability distribution. So some of the noise is 0, some of the noise is positive, some of the noise is negative. You add these numbers and these numbers, you get noisy counts, right? Some of these noisy counts now, you'll notice, are negative, which looks weird because it's like -1 people live in this block. And then there's this post-processing step. And the post-processing step, for the purposes of the intuition I want to build for you, help you build now, does two important things. One is it makes counts non-negative. So here you can see that this -1 got pushed up to 0. And the other thing is it makes the counts consistent with the counts from the higher level in the hierarchy. So all these counts are sort of changed so that the noisy populations in the blocks add up to the noisy population in the block group that was computed in the previous step of the iterative algorithm. So that's sort of how it works. It's much more complicated than that, but that's some good intuition for it. And the noise here, at least at like scales, bigger than blocks or in places that are not extremely sparse, the noise is pretty small. So this is all counties. All of this is counties, and so this is from some census publication. Here it is, which tells you sort of the scale of the noise. Middle 90% of the noise for county populations that came from top down, and you can see it's sort of in the single digits of people. Right, this is like in units of people. Quite small. And here are some other sources of noise, census estimates as to other sources of noise. And sort of the middle 90% is in the hundreds or thousands. And even the mean magnitude is in the hundreds. So it's sort of completely different scales. Great. So as Moon mentioned yesterday, there was an outcry from many data users, and some people said that this was what did you say? I had the quote written down, but I think I deleted it. We have to destroy the data in order to save the data. Was one person's take. Great. So what did this look like? Again, a lot of this sort of happened on Twitter. Ruggles posts a tweet. I'm increasingly convinced that DP will degrade the quality of the census data available about the population and will make scientifically useful public use microdata impossible. I do want to say that I'm going to try to be careful. Sometimes I mess up. I'm going to try to say the top-down algorithm, because the top-down algorithm and differential privacy are different types of things. They're different categories of things. But if I say DP, I say it. But what we're thinking about is the top-down algorithm specific as a specific instantiation of a DP style approach. In any case, so what's the sort of the question here? The question is, I think, the big question. So here's this sort of whole pipeline, a cartoon whole pipeline from there are people in the world to Moon is going to draw some maps. Right. So what happens is there's population, that data is collected. The census sends you mail and sends people to knock on your door. Those are the raw responses. That data is then cleaned. And the result of that is the census edited file. That census edited file goes through disclosure avoidance. This is the top-down step, the differential private step, what used to be swapping. The result of that is the result of that, it's called the microdata file. And then there's some stuff that the census does internally with this data. They produce data products. And then those data products are used by people outside to, learn about the world and describe the world and then make decisions. And what we really care about, I'll posit, is you want to know how design decisions here affect the policy outcomes here. That's sort of ultimately, if you only care about one thing, maybe that's the thing you care about. At least that's the thing I care about, if I only care about one thing. And so what's an example? Can I get, yeah.
Do the Ruggleses of the world also only care about policy outcomes, or do they care about things like statistics as well?
I think so. I think I don't want to say what other people care about. I do think the in the same way that Christina yesterday said that the ad tech marketing managers don't know what to do with, like, they're used to having certain data and they're used to using it, and they're not used to thinking about that data as not statistically valid. That's the same. That also describes sort of census data users. And I do want to be very clear that some users of census data are sophisticated, statistically sophisticated, and some users of census data aren't, but should be. But some are not and sort of shouldn't be. So I had a conversation with a guy who's the demographer for the city of Cambridge. And what does the demographer of the city of Cambridge care about? He cares about renovating playgrounds, because he wants to know where the kids, like, what are the neighborhoods that are having kids and have young families, so that those playgrounds can get budgeted $1 million to get a new playground there 5 years from now, right? I don't want him to know about differential privacy, frankly, right? Like, his life is complicated enough. He cares about elder care and handicap ramps and playgrounds. And so that guy, like, has a very valid, grumble, and he shouldn't have to know about, p-tests and confidence intervals, and I don't know. Maybe that's an opinion. You can disagree. In any case, so I claim that this is the question. And so just some examples. The one data product, and the data product I'll talk mostly about, is the redistricting data. This is all the data that Moon was using. Another example, which I'll mention very briefly, is something called a small area income and poverty estimates. Basically, like, how much money are certain small neighborhoods and areas and rural areas making. And these estimates, this is a census data product. They directly are fed into a formula, and that formula goes to allocate billions of dollars sort of over years. Maybe it's hundreds of millions of dollars. I think it's billions under Title I funding. And then eventually all this data also goes to inform the design and execution of later census sort of data collection and processing efforts. So something like the American Community Surveys, my understanding is that some of the sampling design and the post survey stratification and stuff is informed by the 2020 census data. And all of this data goes on to inform basically all of social science and all of policymaking. And what I want to, and so the challenge here, if that's what we want to study, you know, from here to here, the challenge is that all of this is sort of, for people outside the Bureau, all of this is pretty unknown. Right? Exactly how this cleaning happens, it's not really known. We don't have access to this data set at all, right? This is the thing that has to be kept confidential. We don't have access to the raw responses. These are unknown things. Makes it hard to study. It's also hard, challenging, because the disclosure avoidance algorithm, the top-down one, is really complicated. So there's papers that describe it. There's a code base. It turns out actually getting that code base to run on any data is pretty challenging. And so I've tried, I'm not the coder myself, but I've worked with people who've tried. I had students try. They managed to get it work like a couple times, but then, you know, there's configuration errors on the Amazon EC2 instance, and they're completely mysterious, and it's very hard to actually like get this to run 100 times or 1,000 times in order to do statistics, right? Because what you really want to do is you just take the data set, you run this algorithm 1,000 times, and you learn about what it does, right? And then carry out this whole pipeline. But we don't have the input data. It's very hard to sort of run the top-down algorithm, and it's complicated enough that it's hard to just think about it from a theoretical point of view. And also these internal analyses are often inscrutable, at least for me. I've tried very hard to understand how the small area income and poverty estimates are made. And as far as I can tell, there's just, it's a complete, what do you call it? A mathematical thicket. It's a policy thicket. I could not access it at all. This is not true for the redistricting data. The redistricting data is a simple aggregation of certain data. So we do know how one of these is made. But it makes it very difficult to study this, the question, which is, how does the design of the disclosure avoidance algorithm affect downstream policymaking, right? We don't know what's the input, and we don't know what happens with the output, and we don't quite understand what's happening in the middle. So now I'm going to tell you about some attempts at doing this. This is what I call the quagmire. It's both a methodological quagmire, because you have to figure out how to deal with these problems. And I think that if you're looking for a problem, like if you're looking for a research question in my talk, the research question is sort of how to navigate the quagmire. I'm going to give you a few options that I've seen in work. I think there's theory and empirical questions here. It's also sort of a rhetorical quagmire where people with different goals are trying to ask questions and present their findings in ways that further their own agendas. And so let's journey through the quagmire. So one option, if you're going to try to solve sort of the methodological problem, is to just be the Census Bureau. Not all of us have this option, but it's great. So this is from a paper. I don't particularly care what this table is showing, but the point is they can do this. They can run 25 runs of the top-down algorithm on some input data and report some empirical variance over all the runs, and you can learn things like that. But only the census can do that, as far as I can figure out. Cool. So that's one option. Another option is to have like read the papers and try to just understand what the algorithm is doing. And so here's a wrong but useful model for how to think about what top-down algorithm does, which is going to help explain some of what we're going to see soon. So noise is added to geographic units, counties, tracts, blocks. And this noise is, roughly Gaussian, where this parameter rho depends on the geo unit and the statistic that you're interested in. And then, as I said before, you post-process this to make sure the counts are non-negative, and they sort of add up to consistent in this sort of top-down way. And so what non-negativity gives you is that small counts, if they go negative, they have to be pushed back to 0. And so the error added to small counts is biased positively. And when you combine that with consistency in a place where there are small counts, like if you're looking at blocks within a block group, and some of those blocks are very sparsely populated, then the very populous blocks, those large counts are going to get biased negative because they sort of have to compensate for the small counts. So this is like a useful but wrong mental model. And it's actually I was very surprised by the following. I tried to understand how good was this description, at least the first line. So if you go to Wikipedia and you look up what's the expected magnitude of a Gaussian random variable, because I had to go to Wikipedia, you get that it's this expression. And then you could look at tables like this that the census has put out about how the privacy budget, this row, was sort of allocated across different levels of geographies and different queries. And so you can say the row for the total population statistic at the county level. You just look up this in the table, you get a value of 0.213. You plug it into this expression, you get that your expected magnitude of error is 1.73, right? You do the same thing for a tract and you get 1.97. And then you could look at some example census data that they've put out, some example demonstration data, which I'll talk about in a second, they put out, and compute this average across every county in the country of the error. And you get 1.74, which is remarkably close. You could do the same thing for a tract and you get 1.92, which is also, I would say, pretty remarkably close for such a really bad mental model. Useful. And so I think if you force me to say, it seems useful from what little I've played with it, it seems useful when you're looking at the sorts of geographies where these small counts don't come into play that much. And when you're looking at statistics, simple statistics like total population, 10 minutes. Okay, cool. Okay, so that's another option, just sort of try to reason and build some intuition for what's going on. Option 2 is use the demonstration data. Most of the work studying the effects of the top-down algorithm has been of this type, where they've looked at the demonstration data. What's the demonstration data? Well, we have the real data that was published, the published data from 2010. So there's the 2010 data, it went through the 2010 disclosure system, 2010 MDF, 2010 aggregations, right? That has been public for 12 years. The census, in order to try to get feedback on the new disclosure avoidance system, said, well, let's put the same data through the 2020 disclosure avoidance system and publish demonstration 2010 data as if that data had been privatized using top-down instead of swapping. Right? And so you can look at these two data sets, right? That's what I did on the last slide that was down here. And so what you can do is you can sort of look at these two data sets and compute some descriptive statistics. That's sort of what I did just a second ago. I do want to caution you that you learn about the difference between this disclosure avoidance system and this disclosure avoidance system, right? You can't access just the effects of this, only the difference between this and this. And you can also redo prior analyses and say, okay, we used this data for 10 years and we did lots of stuff with it. Let's redo that stuff and compare the results of those analyses with this data and with this data and see what changes. And the caution here is you learn sort of about the effect of changing your data, adding noise to data, which could be, you could say that that's the effect of the disclosure avoidance system. You could also say that that's the effect of a very brittle statistical analysis. And so we'll see some of that in a second. So if you look at the demo data, you see this bias from non-negativity, which I hinted a few minutes ago. So this is from some old demo data. This is from some newer demo data. This is two different papers a couple years apart. And they basically say here, don't worry about what exactly is on the x-axis. On the left is racially heterogeneous places with a lot of different populations represented, different racial and ethnic groups represented. And on the right is places with basically one race in that I think precincts here, and I don't remember what these are. Tracts. They're like enumeration something. There's some word in 1940s, but they're tracts. Yeah. And what you see is exactly this thing that when you have there's this correlation where where you have the small counts here. I say small counts are biased upwards here. So what are the small counts? They're the empty cells in that, say, precincts population. So if that precincts population is like the white population, the black population, the non-white Hispanic population, the Asian American population, if you're on the right side of this picture, most of those are 0, and those counts get biased upwards. So the total gets biased upwards. And if you're on the left, they're all sort of far from 0, and to compensate, those things have to get biased downwards. So that's exactly what we're seeing. It's my understanding of what we're seeing here. You can rerun, past analyses. So this is from a paper, and they say, well, the top-down algorithm is going to destroy our understanding of mortality rates from COVID, right? So what do? They look at, they take a county's population. They also take broken down by race and ethnicity. So here's the non-Hispanic Black population of a county. They take the mortality rate for that group from COVID, let's say in 2025 or so, in some month in 2020. They divide the two numbers. And they compare that the difference of the mortality rate with the published data and the noisy data, the demonstration data. And they say, look, for small population counties, our understanding of mortality rates is like wildly different, right? So they find that the implementation of differential privacy will produce dramatic changes in population for racial and ethnic minorities, small areas, significantly altering our knowledge about health disparities. But I claim that this is a story about brittleness to noise. And so here's another plot that I made myself, where you just take X, you take some number X, you plot log X on the X axis, which is what they did. You plot uniform noise from -30 to +30 divided by X, which is sort of, if you figure out what's going on here, that's exactly what's going on. It's sort of, this is the noise, the difference between the two data sets divided by the population. So what this tells you is that this analysis, whatever they're doing, is highly affected by noise on the scale of 30 people. So if let me translate that. What they're saying is your understanding of the non-Hispanic Black mortality rate from COVID in counties with very small Black populations is extremely brittle to noise on the order of 30 people. All right, so I think like the wrong lesson was derived, or this was wielded to the wrong ends. I have another example I'm not going to tell you about. So a third option, if you're trying to do the methodological quagmire, is to try to run top-down anyway. Just do your best. And so this is something that Moon and I did with some students, where we couldn't get the real data, so we tried to reconstruct census data ourselves. We didn't have access to the production version of top-down. It wasn't public yet. We used an old version of top-down. We were able to get running somewhat, and we used sort of a simplified model based on papers and the not good but wrong but useful model. We ran these things many times and were able to derive statistics and do the sort of studies that we wanted to do. So here's an example, and I'm totally going to run out of time. So I think I'm going to leave the lawsuit. I was going to tell you all about the lawsuit, but I want to tell you this instead. So one of these analyses that Moon mentioned was this Jingles tests, part 2 and 3. You run a fairly standard statistical package. So here's one of the things you can do, or you do in those analyses. It amounts to a linear regression, where on the x-axis you have the Hispanic population, where each of these now I think is a precinct. It's a precinct. And on the y-axis you have that precinct, the share of that precinct that voted for a certain candidate. So this is a certain race in Dallas County for Texas governor, where the candidate was Lupe Valdez. And so it's this dot has 60% Hispanic population in this precinct, and 40% of that precinct voted for Lupe Valdez in 2018. And this y-intercept represents, under this method called ecological regression, is interpreted as the Hispanic support for this candidate, Lupe Valdez. Now, as Moon alluded to, you can worry that if you add noise to the census counts, in particular, you're adding noise in this direction on the Hispanic population, you're going to add noise to this signal. And in particular, you're going to attenuate it usually. And so what can we still detect racially polarized voting? And so in our paper, we sort of looked at this effect and showed that indeed, you know, it looks like there's a bunch of noise if you just do the old thing, but you can do very simple things in order to sort of recover the previous sort of robust version. And in particular, if you just ignore precincts with small numbers of votes, 24% of precincts in this case, then you recover sort of the noiseless linear regression. You don't have to just ignore those precincts. You can do weighted linear regression. That's sort of maybe the more disciplined thing. So you can see sort of the effect of these precincts here, which is sort of all noise, and just as noising this regressor is removed here. But you can do weighted linear regression instead. And when you're in Dallas, it's not such a big deal. Maybe when you're somewhere much smaller, this is Brazoria County, the noise from top down, if you're sort of ignoring it and running previous analyses unthinkingly, is significant. But if you do sort of anything reasonable, that noise is no longer significant. I'm going to skip this. I'm going to just point out again that in this paper, which is about the Title I funding issue, again, this is a rhetorical thing more than anything. They highlight sort of the effect of noise on their analysis is in the tens of millions. But when you compare that to other sources of noise that are quantified and estimated by the census, it's a drop in the bucket. And when you compare it to the total amount of funding, it's even sort of a smaller drop in the bucket. So yeah, I don't know. This is maybe a lesson in ways of communicating and to what ends. How much time do I have? No minutes. All right. So suffice it to say that there was a lawsuit that I wanted to tell you about, where the census was releasing purposely flawed population tabulations, which is a fun way of describing it. And the outcome at the end of the day, there's lots of interesting questions, which I'm happy to talk about. The outcome at the end of the day had nothing to do with differential privacy and had everything to do with just sort of basic 1L points of law. In particular, Alabama had no standing to sue. And the court's reasoning to say that they had no standing to sue for like each of these points, it's actually very interesting. Again, I'm happy to talk about it. So future directions. We need more work. There's a lot of empirical and theory work, and Philip will also tell you lots of other things that you can do to help and to contribute.
Great, let's thank Aloni. Well, we have time for one question while Shuchi sets up for the post to presentation announcements. Anyone have a question?
This is a pretty general question. Well, thanks for the talk. Really enjoyed it. It seems like a meta level thing that is going on is a lot of reproducibility. And I'm wondering if through like building toy down, if there's any lessons on reproducibility or best practices that are gleaned from this process.
I think that's a good question. I agree that reproducibility is a part of what makes studying it really difficult. It's challenging to think about how you might provide the Census Bureau might provide reproducibility in a setting where your hands are tied by stringent confidentiality requirements. In particular, the data can't be known. The input data can't be known. That's the whole point. You could do better about having a easier to run top-down algorithm. But still, that's that's only part of the story. And the other part of it is just there's 1,000 ways that there's more than 1,000 ways that the data ultimately gets used, either internally at the Bureau or externally by social scientists or economists, or basically every empirical paper uses this data in one way or another. And sort of, I think you would have to solve the reproducibility issue for all of those works in order to understand really the downstream effects.
Thank you so much. Without taking too much time into our next break, I want to give a very brief preview of the posters we have this afternoon. So please come to the poster session. It's at 4 to 5 p.m. On the second floor, and we'll have tea just before the session at the same in the same space. So everyone's welcome to come. So what we'll do is we'll do a quick run through all the posters that are going to be presented, and when your name shows up, the student in the audience, please just stand up, introduce yourself, introduce the title of your poster really quickly in like 15 to 20 seconds. Let's see how quickly we can go through this. And this is in reverse alphabetical order by last name, just to keep you all on your toes. So here we go. So Zishing.
Hello everyone. My name is Zixing Xu. I'm from UIUC, and the work I'm presenting is called Personalized Pricing with Group Fairness Constraint. It's a joint work with Professor Xing Chen from Georgia Tech and Yuan Zhou from Tsinghua University. Welcome everyone to attend my poster session this afternoon. Thank you.
Thank you. Anna.
Thank you. My name is Anna, and I'm happy to present our poster on algorithmic bias and homophily in link analysis ranking, mostly related to web search applications. This is work done partially with my advisor from Columbia, Augustine Chantreau, and partially here at Simons with Amin Saveri too. Some of it is still ongoing, so we very much welcome feedback. Thank you.
Thanks, Roshni.
Hi, everyone. My name is Roshni, and I'm a third-year computer science PhD student at Stanford. My research focuses on developing statistical frameworks for data-driven decision-making. And the poster I'm presenting today is called Learning from a Biased Sample. And this is joint work with Li-Hua Lei and Stefan Wager at Stanford.
Thanks, Fernando.
Hi, everyone. I'm Fernando Rodriguez Santisteban from Stanford also, MSME. The poster I'm presenting is improving organizational decision-making in nonprofit organizations using a decision analysis framework. It's the co-authors are Ross Schachter and James Sweet, also from Stanford.
Thanks, Seyong.
Hi everyone, I'm Seyong from Columbia University. I'm a third-year PhD student in computer science department. The poster that I'm going to present today is about differentially private synthetic control. As the name can tell, it's synthetic control is a causal inference method, and we made it differentially private. Thanks.
Thanks, Juan.
Hi, I'm Juan. So I'll be talking about work in performative prediction and new solution concepts in performative prediction. This is together with Mike Kim, who is here at Simons.
Thanks, George.
Everyone, I'm George Norov. I'm a PhD student at UPenn. And today, my poster will be about how to categorize scoring rules, not just according to if they're proper or not, which incentivizes truthfulness, but also to what extent do they incentivize reporting of precise estimates. So we encourage the expert to perform a lot of sampling from the underlying distribution if they want to report back the estimates, and what scoring rules are good for that.
Thanks, David or Priyanka.
I'm David, and this is joint work with Priyanka, who's also here. This paper is a little bit different. We basically read a bunch of the NeurIPS ethics reviews and broader impact statements, and then summarized what we found. So come learn about that.
Thanks. Yuan Tong.
Hello, everyone. My name is Yuan Tong Li from UCLA Department of Statistics. And today I would like to present the rate optimal contextual online matching mandate with an application into the job market. Yeah, thank you.
Thanks. Cheng Wai.
Hi, everyone. I'm a PhD student in operations management from Duke University. I'm going to present the poster titled "The Blockchain News Vendor: Value of Freshness, Transparency, and Smart Contracts." It's mainly about blockchain applications in fresh produce industry to reduce food waste. This is joint work with my advisors, Boyle and Jeanette.
Thanks. Devansh.
Hi everyone, I'm Devansh. I'm also at Stanford, and the paper I'll be presenting will be on balancing efficiency and fairness in traffic routing. And so this is essentially looking at the problem of routing road traffic from a perspective of not only achieving system efficiency, that is trying to reduce traffic congestion, but also achieving certain fairness properties in the process as well.
Andrew. He's not here. Evangelia.
Hi everyone, I'm Evangelia and I'm a 5th year PhD student at University of Wisconsin-Madison. So my poster will be about online learning for Pandora's box and mean some set cover. Basically, it's a follow-up on some other work we have with Suji and my advisor, Christos Zamos.
Thanks. Bailey.
Hi, my name is Bailey. I'm a PhD student at Carnegie Mellon, and I'll be talking about work that's joint with Ariel Prakasha and Sven Wang. Basically, we generalize the standard model of voting to allow voters to behave altruistically, which means that they account for the common good in how they vote. And we show that this can have really positive impacts on the outcomes of elections.
Thanks. Kate.
I'm Kate Donju. I'm a PhD student at Cornell, and I'm be talking about models of fairness and federated learning, which is joint work with my advisor, John Kleinberg. We look at sort of federated learning, so agents that have data that's distributed among multiple different locations, and they're each trying to use this data sort of to build a model that has high performance on their own personal data set in collaboration with other agents. We look at questions of fairness, meaning like differential levels of error rates that these different agents obtain.
Thanks. Mihaela.
Hi, everyone. My name is Mihaela Kurmei, and I'm a 4th year graduate student at Berkeley. Broadly, my research is on understanding dynamics of interaction between algorithmic decision makers and human decision makers. In this work, we're looking at the impacts of link recommendations in social networks, particularly showcasing how they might have unexpected effects when measured in a delayed time frame, and how they can have indirect effects that are very unexpected with respect to the short-term immediate effects.
Thanks. Andre?
Hi, I'm Andres Cristi. I'm a 5th year PhD student at Universidad de Chile. In this work, we ask how to make fair decisions if we are hiring people sequentially, like in the secretary problem. I hope to see you at the poster more about it.
Thanks. Sarah?
Hi, my name is Sarah Sen, and I'm a 5th year PhD student at MIT. And I'm going to be talking today on regulating algorithmic filtering on social media, where algorithmic filtering is the process used to curate content, and it's going to be a sort of regulation and auditing framework. This is joint work with my co-advisors, Alexander Madry and David Bradshaw.
Thank you. William?
Hi, I'm William. I'm a PhD student at Columbia. I'm presenting some work on a model for studying feedback loops and recommendation systems, particularly when you're showing users menus of items and looking at what sorts of regret benchmarks are feasible, what assumptions you need, and connections to diversity of recommendations. This is joint with Arpit, who's also been around this semester.
Thanks. Robin.
Hello, I'm Robin Bowers. I'm a second-year PhD student at the University of Colorado Boulder. I'm presenting joint work with my advisor, Bo Wagner, called High Welfare Matching Markets via Descending Price, which is sort of an auction-inspired spin on matching markets with money.
Okay, and that brings us to the end of this session. Thank you very much. Please do come to the poster session this afternoon. And we have a short break outside. We will get back here for Philip's talk a little past 11:30. And please also use the opportunity to ask Moon and Aloni any questions that got left. Thank you.